Good morning. Welcome to Thermtest's latest webinar, the Anisotropy of Thermophysical Properties in Extruded Polymers. Try saying that 5 times fast, am I right? I'm Angela. I am your host again for today's illuminating session. So in this upcoming webinar, we will delve into the fascinating subject of anisotropic thermal properties in extruded polymers. We'll explore how the modified transient plane source, MTPS sensor, can be utilized to measure these properties accurately. This session aims to provide valuable insight into the capabilities of the MTPS method for future research and thermophysical analysis. I'm excited to introduce our distinguished speaker for the event, Dale, the president of Thermtest. With over 2 decades of experience in thermophysical instrumentation, Dale's expertise makes him an authoritative figure for today's webinar. As always, we have allotted time for a Q&A session at the end, so if you have any questions during the webinar, feel free to type them into the chat box, and Dale will address them at the end. Now, let's get ready to immerse ourselves into this intriguing world of thermal analysis. Over to you, Dale.
Thanks, Angela. Hopefully everybody can hear me okay. As a good introduction, there is one thing that I like to comment on, that I'm in a unique position to benefit from technical knowledge and application knowledge from such a wonderful team of physicists, application scientists, and engineers here at Thermtest. So although I'm presenting on a topic I'm familiar with, it comes from a wealth of knowledge around our team in terms of the measurements we make and support we provide to our customers. So the topic we're talking about today is the anisotropy of thermophysical properties in extruded polymers. There was mention of an MTPS sensor and the measurements we do. Actually, most of these measurements were done symmetrically, but certainly I will touch on the asymmetric or the absolute version of the MTPS sensor and how it can be used to measure the same. It certainly has the same sensitivities and accuracies, and those are the topics we'll talk about. So this is under polymers and composites, which is one of the unique capabilities of the testing we do with the transient plane source that is part of the Thermtest thermophysical family, and we'll talk more about that. So the contributions, again, commenting on where does our knowledge come from? It comes from many years of experience in this industry, as well as a team around us. So some of those leads are David Langer, our lead physicist, Renzo, one of our part of the physics team, and Kelsey is our lab lead. And there's certainly a great group of people around that provide insight and wisdom and how we present data, so that we have contributions that are valued to the industry. So we get to the next screen. So what does Thermtest offer in terms of thermophysical measurements? We have basically a suite of instruments that are both steady state and transient, both for solids, liquids, and pastes, powders, depending on what's the most suitable method for your application. There's a quick snapshot of those, and those are both come in laboratory form as well as portable form. Again, based off economics and capability, we've sort of categorized them into 2 areas. If your application is outside of the scope of the discussion we're having now, please get in touch with us, and we can certainly talk about why steady state or why transient might be better suited for your application. So the measurement platform series is basically a broad range, after almost 20 years of measuring thermophysical properties, thermal conductivity, thermal diffusivities, and specific heat. Our concept and how we approach measurements and required instrumentation is really around primary design, primary purpose, meaning a sensor or method is specifically designed for that application. So we've broken those down into 2 central areas: transient plane source for solids, pastes, and powders, transient hot wire for liquids, and additionally phase change materials. And all of those sensors are available on our 3 main measurement platforms, MP, that's what that stands for. The 2 we're going to talk about today are our MPV, which is versatile, that's our mid-range instrument, and our MP1, which is our future-proof advanced sort of thermophysical instrument that we've brought in as our two main testing instruments. The third one is our economical MP2, which is our portable version, which again has the same two primary methods as well as some other methods available, but we've made those two primary methods available for all testing. So as you can see below at the bottom of that PowerPoint, there are some associated standards, international, for the testing that those measure. So a little bit of background or theory on the transient plane source. It is a double spiral of nickel encapsulated in polyamide or Kapton. The sensor generates heat. The active test area is within that square, that double spiral. When a measurement is made, a current passes through these two principal contacts, and we simultaneously sense electrical resistance. Because there's a current passing through that double spiral, it generates a heat. Typically above ambient temperature, it's less than a few degrees. And so while it's generating heat, we're monitoring the electrical change in resistance, which gives us a plot of temperature rise versus time. That's our raw data. So regardless of a transient hot wire, although the construction of the sensor is different, in this case, this is a flat sensor that can be used symmetrically or asymmetric, which we'll mention about. That's how the raw data is generated, that we're recording the heat of diffusion as the heat is being pulled away from the sensor and diffusing into the sample, and look at the electrical change in resistance. So therefore, the lower the slope, the more conductive; the higher the slope, the more insulated that sample is. There's a couple key requirements once we've generated raw data, and that's to remove the contact resistance between the sensor and sample. And on the MP1, that's automatically done. We characterize the contact resistance. That's very specific to the Thermtest MP1. And the back end of the data, that we are not hitting any boundaries of the sample. And that is one of the main assumptions of the transient plane source method, is that the sample is semi-infinite. So for the measurements we're doing as part of this presentation, there is an extension of the transient plane source that allows for measurements of anisotropy. So that would mean your sample has a filler or some type of repeating layer through the thickness that basically heat spreads in two directions differently. So acts through the thickness and in plane. The assumptions of this are that the two principal directions are isothermal within themselves, and that the radial direction is perpendicular to the sensor, and that you know the input of specific heat. It is important also that the anisotropy is well organized through the thickness. That means that your filler or your layering is repeating, so that the anisotropy is not time sensitive. So at different penetration depths, which is defined by the length of time you measure, again, we measure the thermal diffusivity in both directions. So we have a penetration depth that we want to make sure stays within the boundaries available. So if we can do different time scales, then certainly the assumption is met if that result stays stable. So the module, and that's what we refer to it as, an anisotropic module. The radial diffusivity and the bulk conductivity can be attained from the temperature response of the sensor. If the volumetric specific heat is known, you can get the additional properties. If the volumetric specific heat is not known from rule of mixtures or measurement by DSC, there is an available specific heat module that directly measures specific heat. There are some advantages to that over a DSC, and that is that it's measuring a larger sample, which can be advantageous if you're measuring heterogeneous material or materials that are constructed in such a way that you can't locally cut a sample out for a DSC, such as a battery, pouch, or cylinder. So these are some of the, once you know specific heat, the volumetric specific heat, these are the mathematical representation of the other directions that the results are taken from. So what you end up with is axial or through thickness, thermal conductivity and thermal diffusivity, and in plane or radial thermal conductivity and thermal diffusivity, and a penetration depth based off the time used for each of those two directions. So because you know your two penetrations. With calipers, you measure the thickness and you measure the sample dimensions. You can get the available probe depth in both directions. We want to make sure that the assumptions are met, that we stay within those two directions, which is just based off the change of time. So the two samples we're measuring are two polymers, and we're using the Anisotropic Module. The two polymers are Torlon, which is a brand. It's a board shape. It's a polyimide. It's typically used for it's a high temperature polymer. It can be used in friction applications. The sample set we have are 50 millimeter in diameter by 6 millimeters thick, and again, symmetric. And Nylon 66, which is a extruded rod versus an extruded board, like the Torlon. That sample, so we took a rod and cut discs out of it. Those two discs are 38 millimeters in diameter, which is the diameter of the rod, and 10 millimeters thick, which is the sections we cut. Again, symmetric. Torlon, as it's a board shape, we measured that where the board direction, the extrusion direction, was sitting parallel to the sensor. We measured the volumetric specific heat with the TPS specific heat module. You can see that the axial thermal conductivity is in good agreement with the vendor supplied C177, which is a guarded hot plate. There's only about 2.5% difference. The guarded hot plate is a steady state through thickness value only. That's ASTM C177 again. You can see in the table, we get the additional properties of the in-plane. And of course, this being extruded board, we are getting anisotropy based off of the effects of extrusion and the composition of the material itself. But certainly the direction of extrusion does provide or enhance that anisotropy created by the board shape. And there's a reference to the C177 data if you want to investigate. The other type of sample is Nylon 66. Again, it's rod shape. So we wanted to get, because extruding, you have different shapes of extrusion. We wanted to sort of investigate a board shape and a rod. Nylon 66 is a good candidate because of the available thermal conductivity. When you Google Nylon 66 thermal conductivity, you can get a wide range of numbers. We measured the specific heat directly with the TPS specific heat module, and we wanted to correlate to another method. It sort of gives us confidence in our data and allows us to demonstrate like this. Of course, that the board, we don't have vendor data on this using C177. That was what we had with Torlon, because the pieces we had with Torlon were certainly not large enough for guarded hot plate or C177. That's typically a 12-inch disc or a 12-inch square to be able to measure that. So as we didn't have vendor data on 66, we were limited to this 38 millimeters diameter. So what we did was cut LFA samples, which are 10 millimeters square, into the rod. So this being my coffee cup, let's say that is the rod shape, Disney. We cut 10 millimeter squares into the sample, and that gives us a equivalent radial thermal diffusivity that we can use in the specific heat calculate the thermal conductivity. So you can see if there is anisotropy in the Nylon 66 due to the extrusion, and you can see how that correlates to the anisotropic measurement from the TPS. So our in-plane, so again, that being a disc shape, it would be in-plane 0.33 versus LFA in that same direction, 0.33. We didn't do LFA pieces through the thickness. We thought rather correlation to one direction was pretty good for this presentation, to at least show promise and the accuracy of all the data. So you have a smaller amount of anisotropy, but yet it's still there. So it's important to sort of recognize it, that if your values are varying between 0.33 and 0.35, and the other measurement that you can make with the TPS is actually a bulk measurement. So if you were to measure this with a bulk standard measurement, three-dimensional value, you would get a number between 0.33 and 0.35 for that particular sample. That is not saying that every extruded rod of Nylon 66 is the same result, but there are reasons that bulk values vary. And if you have the right tool set and the right experience, and that's sort of what we're good at, certainly anisotropy could be one of the reasons why your values aren't lining up with expected, or that you're getting sort of location anisotropy. That's part of what we're really good at in our team. Conclusion, the rate of cooling of polymer upon extrusion can affect its crystallinity and affect the anisotropy, and thermophysical measurements can demonstrate that. Torlon, being a board shape, has well organized anisotropy. That's why we get a fairly decent correlating value with a steady state method, which is absolute, meaning through the thickness and through the thickness from guarded hot plate and axial from the TPS lineup. Nylon 66, again, fairly well organized anisotropy, just because we have good correlation of a small sample set from another method that shows pretty good cooling uniformity in an anisotropy. Yeah, I guess I didn't mention that if you Google Nylon 66, there's a question. This is question time. I'm just jumping into that, Angela. Hopefully it's okay. That range, you can see anything from 0.29 to 0.36 watts per meter Kelvin, and maybe even a little lower. Some of that, again, is just, Nylon 66 made by different companies, but certainly anisotropy can be, a very specific effect on the values that are measured by various methods. So again, transient methods, they're measuring either a bulk property, where you are not defining any direction, it's just the natural heat. That value, it's suggestive of the true values, but certainly if that value is important to simulation or to an application, you might want to understand it. It's anisotropy. And then other methods might be more uniquely qualified for higher degrees of anisotropy or heterogeneity. For higher degrees of anisotropy or heterogeneity, meaning that the sample's anisotropy is not well defined. So the filler or layers are non-repeating through the thickness, meaning if you measure different time scales with a transient method and you get varying results, the assumptions of that method are going to be broken and create errors in the results. Moving to a steady state method like a guarded heat flow meter or a heat flow meter, those are standards, ASTM standards E1530 and C518. There are, of course, equivalent ISO standards, might be better suited. And that measures resistance across a very specific controlled one-dimensional shape. So it's a very high confidence value, and you get a really high confidence one direction. So certainly for anisotropy, you can cut samples or print them, or whatever is creating an anisotropy in your sample. You can certainly align those to the direction and measure those direction. So there's any other questions? Otherwise, that's the end of the presentation. I leave this slide up as we are hosting ITCC at the end of October 2024. We invite everybody who's interested in the area of thermal conductivity. This is a more than 60-year conference that is very focused on thermophysical properties in various methods of measurement and application. So it's a good one to keep an eye on.
And I think we'll make sure it's a good time though, too, right, Dale?
Yeah, that's what. Yeah, we're the host of it. Us along with another team in Virginia, Laser Thermal, who does thermal optical methods of measuring the same type of properties we measure. So should be a good conference.
Well, I don't think we have any more questions. Do you have anything else you'd like to add?
No, hopefully the last points are really to consider anisotropy. If you're measuring bulk for everything, one more sort of technical tip that I like leaving, if you're measuring bulk properties and the volumetric specific heat that you're calculating from your three-dimensional or bulk property doesn't line up with your direct measurement of specific heat by DSC or specific heat module, that can be a sign of anisotropy. So that might be good to investigate that further. The reason why is specific heat is a mass or volume-based property, so that has to be measured directly on an anisotropic sample. So it's a good sign that your sample might be anisotropic. And those, you know, if you're looking at a TPS method, whether it's the MPV or the MP1, those both have scalable, meaning you can look at bulk and add the ability to measure anisotropy or a specific heat at any time as that need arises. So you have a tool set to investigate whether or not your samples are anisotropic.
Very cool.
All right.
Well, I guess thank you everyone for participating in today's enlightening webinar on anisotropic.
Yep,
I was saying anisotropic before. Anisotropic, okay.
Yep.
Thermal conductivity of extruded polymers, and a heartfelt thanks to you, Dale, for imparting your invaluable knowledge on this complex subject.
All right.
Keep an eye on your inbox for the recording of this webinar. We'll be sending that out in a couple of days. And if you have any questions, please don't hesitate to reach out to us at marketing@thermtest.com, and our dedicated team will happily answer any questions that you have. Don't forget to mark your calendar. We have our next webinar scheduled, and that will be on September 19th. And that will be exploring thermal conductivity of polymer films using the MP-TPS method with Dr. Jagannath Sripatta. And registration will open likely later on today or tomorrow. So I wish everybody a wonderful day, and remember, stay curious.